At the age of 16, Albert Einstein asks a simple question. What would happen if he ran as fast as a wave of light? Would the light wave appear to stand still? When he returns to this image less than 10 years later, he will revolutionize our understanding of space and time.
He loved to imagine worlds that didn't exist. That was his power, the power that he could see things physically in a picture, things that other people couldn't see.
The man who makes these breakthroughs is an absent-minded professor, a twinkle-eyed lover of humanity. But he's also selfish, has 2 failed marriages, and confesses himself an emotional failure. Albert Einstein is born in 1879 in southern Germany to middle-class Jewish parents. As a child, he is quiet and withdrawn.
His parents began to think maybe he was retarded because it took so long before he began to speak. But he was just busy thinking, apparently.
As a young boy, he is fascinated by puzzles and games and shows remarkable perseverance. At age 9, he builds a tower of cards 14 stories high.
By all accounts, Einstein as a child was a nerd. And as a consequence, the other kids would make fun of him. He was apart. He lived in the world of books, the world of ideas.
In 1896, the 17-year-old Einstein wins admission to the ETH, the MIT of Switzerland. Like Galileo, he is witty and sharp, with a sense of humor, and is also a rebel. Einstein has resolved to become a theoretical physicist, but he feels stymied. His physics professor, Herr Weber, has no interest in the latest cutting-edge theories of light and electricity. He passes his exams only by borrowing a friend's class notes and graduates with unexceptional grades. His behavior has not gone unnoticed. All of Einstein's applications for jobs at universities are rejected.
After Einstein graduated from the university, he became a loser in every sense of the word. His professor, Weber, actively disliked the young Einstein. He wrote letters of recommendation, which we now know undermined his chance at any kind of academic appointment. Even before he became a physicist, his life as a physicist was over.
Two years after leaving university, Einstein finally finds a job as a clerk in a Swiss patent office. His work is far removed from theoretical physics, but this seemingly dead-end job will be his salvation. In Bern, the 23-year-old clerk quickly settles into a bourgeois existence. He marries Mileva Maric, a fellow student from the university. Luckily, his job is undemanding enough that he can steal time to grapple with cutting-edge questions in physics, such as the nature of light.
Others in such circumstances would have just thrown in the towel and would have given up on a career in physics. You get the sense that this is someone who just was possessed by an intellectual demon and couldn't do other than what he did.
Now Einstein returns to a simple image he first imagined in high school. What would happen if he ran as fast as a wave of light?
Both Isaac Newton and Einstein shared this uncanny ability to create simple pictures that children could understand and extract from that images which changed the universe.
According to Newton, the speed of a light beam should appear slower to someone who runs alongside it. But light does not seem to obey Newton's laws.
Einstein says the light beam moves away from you at the speed of light, no matter how fast you move. You can never catch up to the light beam. You hit the accelerator, you gun the engine, the light beam still moves away from you at the same rate. How's that possible? How is it possible you can never catch up to a light beam?
Now, like Galileo and Newton before him, Einstein ruthlessly questions assumptions that no one else dares. If the speed of light never changes, then something else must give.
Then he had it. Time is relative. Time is relative to the speed at which you move. And that idea shook the universe.
Einstein has discovered that Newton's laws only hold true for the world of everyday experience. When objects travel at speeds close to the speed of light, common sense breaks down. Distances stretch. And clocks tick more slowly. Newton, forgive me, Einstein writes later. At the age of just 26, he topples Newton's laws of motion with his theory of special relativity. With childlike questions and simple pictures, Einstein changed the world. In 1907, Einstein turns to new scientific challenges. But newly published letters reveal a little-known personal side. As he creates his greatest work, he will withdraw within himself, and those closest to him will suffer. Einstein's wife, Mileva, was once a physics student who dreamed of her own scientific achievements. But now, as Einstein lectures and collaborates with others, Mileva hardly sees him. She fears she is losing both her husband and her dream. Then, in 1914, Mileva discovers that she has a romantic rival, Elsa Lowenthal, Einstein's cousin. Einstein's marriage falls apart.
You know, I'd love to have a beer with Einstein, but I wouldn't introduce him to my sister. There was a sense where the rules didn't necessarily have to apply to him.
Einstein will marry Elsa, who's willing to keep house for him with fewer expectations. He's given up on love in marriage. His science comes before all else. By age 35, Einstein is pursuing a goal many physicists believe is impossible. His intuition tells him that there must be a more general theory of relativity that also explains the force of gravity. Like Newton, Einstein is obsessed. For years, he grapples with mathematics of horrendous complexity, unsure whether he is on the right path or a fool's errand.
He famously would worry a problem for years on end, almost like a dog with a bone. Wouldn't let go of the problem.
When he was working out general relativity, he almost had a nervous breakdown. He would concentrate to the point that he lost an enormous amount of weight. He wouldn't eat. He focused on a problem the same way that Isaac Newton focused on a problem.
At last, in the fall of 1915, Einstein realizes he's solved it. His great insight is so strange, even physicists will struggle to comprehend it. He proves mathematically that mass and energy curve space and time. A massive object like the sun warps space and time so much that a nearby planet moves in a curved path around it. To Newton, they appeared to be attracted by a force. But this is just an illusion. The same phenomena holds true on Earth. Objects that appear to be pulled by a gravitational force are actually traveling through warped space-time.
Einstein's general theory of relativity changed forever our ideas about space and time. It is so beautiful, it has to be right.
Einstein arrives at a set of equations governing space-time curvature. These simple lines describe the motion of galaxies and the destiny of the universe.
When we physicists look at the equations of Albert Einstein, we cry. We cry because they are so gorgeous. Realize that the motion of the heavens, with all the curves, spaces, and time warps and what have you, can be summarized in an equation about an inch long. That is power. That is incredible. That is beautiful.
Although Einstein will continue working until the day he dies, by the time he is 40, he has completed his greatest work. Galileo applied mathematics to motion. Newton perfected these laws for everyday experience. But Einstein's search for a deeper theory revealed laws that govern the entire universe. Today, another brilliant rebel is searching for an even broader theory, a theory of everything. No living scientist has shaken the foundations of physics like Galileo, Newton, or Einstein. But among those who have advanced cosmology's frontiers is a once lazy student named Stephen Hawking. Today, he holds the same chair in mathematics at Cambridge University as Isaac Newton.
I was born 300 years after the death of Galileo. I hold the same job at Cambridge as Newton did, and I work on Einstein's general theory of relativity. Of the three, I feel closest to Galileo. He followed his nose and was a bit of a rebel.
Stephen Hawking is born in 1942 in Oxford, England. Like Galileo, Newton, and Einstein, as a child, he is fascinated by how things work. Yet at Oxford University, Hawking hardly works at all. Instead, he relies on his extraordinary facility with mathematics to coast through. Hawking spends most of his time socializing and on the river with his rowing team.
By all accounts, Stephen Hawking was not the kind of person destined for greatness.
At college, Stephen was not the hardest of workers. Stephen himself says that in his entire undergraduate period at Oxford, he only worked about 1,000 hours, which is an hour a day on average.
Hawking is bored and apathetic. Nothing seems worth working for. Yet a tragedy is about to strike that will turn a bored intellect into a passionate mind. In 1962, Stephen Hawking has just begun to study cosmology as a graduate student at Cambridge University. But signs of illness are becoming too difficult to ignore. A slight speech impediment, difficulty pouring a beer. Doctors tell Hawking he has ALS, commonly known as Lou Gehrig's disease. The regions of his brain that control motion are wasting away. There is no cure. The 20-year-old student learns that his body will become paralyzed. His breathing muscles will eventually seize up, suffocating him. Doctors say he has just 2 years to live. Hawking falls into a deep depression.
When Stephen was first diagnosed as being ill, he really didn't expect to live more than a year or two, and therefore there didn't seem much point in even completing a PhD.
But inexplicably, his disease progresses more slowly than predicted. He meets Jane Wilde, the woman who will become his wife, and he finds a purpose. I dreamt that I was going to be executed, he writes. I suddenly realized that there are a lot of worthwhile things to do if I were reprieved. Now Hawking begins working hard for the first time in his life, and to his surprise, finds that he likes it. By the early 1970s, Stephen Hawking is a well-established cosmologist. He is also in a wheelchair. Yet he is remarkably stubborn. Nothing will keep him from living a normal life. He has children, he works intensely, and he is about to make a great breakthrough that will extend Einstein's theory in an unexpected direction. Einstein's theory of general relativity predicts the motion of very large objects such as galaxies. But it cannot explain the behavior of the tiniest subatomic particles that are the building blocks of the universe. Their motion is only predicted by a different theory called quantum mechanics. And to the frustration of Einstein and every physicist since, the two theories appear completely incompatible. Yet Hawking is brash enough to tackle the impossible.
When Stephen Hawking was doing his pioneering work, there were two armed camps. They hated each other. They never talked to each other. On one side were the true blue loyalists, the ones who held the flame of Albert Einstein burning bright. On the other camp were the quantum theorists. They dealt with the world of particles, subatomic particles, hundreds of them, thousands of them, and they didn't talk to each other. They had different mathematics, they had a different language, a different physical picture, and here comes Stephen Hawking saying, I'm going to try to marry the two together. Well, that was heresy. No one had done that before.
Now Hawking asks, what happens if you look at a black hole, a massive object, but zoom in to its smallest scale?
Hawking also, like Einstein, has an incredibly good nose. That he has an intuitive feel for interesting questions to ask and how to ask them.
Black holes are the most bizarre and extreme prediction of Einstein's theory of gravity. Theoretically, if a mass is extremely concentrated, for instance, if a star were compressed into a ball just miles wide, the space around it will become so warped that gravity will keep everything from escaping, including light.
A black hole is a region of space in which gravity is so strong that light can never escape. It's like a one-way membrane in which things can go in, but nothing ever comes out, including light, and that's why it's called black.
Now Hawking attempts something his colleagues assume is impossible. He uses the equations of quantum theory to analyze what happens to tiny particles trapped by gravity on the edges of black holes. By now, he can no longer write. If he was an experimentalist, his career would long be over. But Hawking has rarely even looked through a telescope. And for theory, all he needs is his brain. Like Newton and Einstein, Hawking has great powers of concentration. He reruns long, torturous equations again and again in his head, checking and rechecking his calculations.
He tends to think in pictures, and he tends to start with some idea that he thinks he is right, and he goes from there.
He has to rely upon keen insight and leaps of logic to compensate for the fact that he cannot check every single line.
He just has a tremendous drive, a tremendous determination to get to the bottom of things.
Hawking's results shock him. Black holes are not completely cut off from the rest of the universe as once believed. Instead, their edges shed tiny particles, now called Hawking radiation.
The arguments are so compelling, everyone now agrees that black holes must give off Hawking radiation. The radiation will carry away energy and mass, and the black holes will slowly evaporate and eventually disappear.
Hawking has shown that, like water in a boiling kettle, black holes slowly evaporate away. Just as importantly, he's proven that in one particular case, general relativity and quantum theory can be fruitfully combined.
My discovery that black holes are not completely black, but should glow like hot bodies, was the first example of an effect that depended on both the large and small scale theories.
When the result came out, it was so beautiful. It just had that feel about it. Just talking about it was like rolling candy on the tongue.
Finding a theory of everything, a deeper theory that unifies Einstein's equations and quantum mechanics, is now the holy grail of physics. It would explain the origin of the universe. And Hawking has created new hope that this ultimate puzzle can be solved.
It's clear that Stephen's discovery of black hole radiance was an important piece of the final jigsaw, even though we don't really know what the final jigsaw is yet.
Who were the greatest physicists? They were ugly ducklings, rebels, and nerds, consumed by deep intuition and unafraid to question the most basic assumptions.
It does take a strong ego to say, well, that's not so tough, I can crack that. I mean, the odds are really against you. There's no guarantee that there are any answers out there, that science actually works. You're really taking a huge chance.
Their stubborn persistence revealed deep laws of nature, but their quest remains unfinished. And such brilliant minds come along only once in a great while. Yet who knows? It's possible that the next brilliant rebel is already among us.